When feedback is applied to an amplifier, gain stabilization takes place. It means the gain is no more dependent upon the circuit in which the amplifier is inserted or the point in the circuit where the amplifier is inserted. Feedback also is able to provide stability against the variations in temperatures, against aging, against variation in the parameters of the active elements that are used in the design of amplifiers. Stability of operation is one of the greatest benefits that is able to be achieved with the help of feedback. It remains constant and also it remains known. Feedback also helps us in adjusting the impedance levels of the amplifier, thereby enforcing impedance match at the input terminals as well as at the output terminals. With the help of voltage sampling, output impedance of the amplifier can be decreased. With the current sampling, output impedance can be increased. With the series mixing, input impedance can be increased. With the shunt mixing, input impedance can be decreased. Hence, by proper selection of sampling and mixing circuits, it is possible to adjust impedance levels, thereby ensuring impedance matching at input terminals as well as output terminals of the amplifier. In addition to gain stabilization and matching, feedback is also capable of providing a reduction in distortion. Distortion means deviation of the waveform of the signal while it is traveling through the amplifier circuit. Deviation implies loss of information. Hence, distortion is associated with loss of information, a drawback, a serious issue. When feedback is applied to an amplifier, it reduces the distortion. In addition to distortion, noise that is generated in the amplifier and added to the signal when it is traveling through the amplifier. This noise also gets reduced. This is another advantage. This is another benefit when we apply feedback to an amplifier circuit. In addition to all these benefits so far mentioned, feedback is also able to increase the bandwidth of the amplifier. Analog circuits, feedback amplifiers, part 3, series on semiconductor devices and circuits, lecture number 9.12. Feedback technique is able to improve the performance of amplifiers. This improvement is achieved by adjusting the input impedance and output impedance of the amplifier with the implementation of feedback. By selecting appropriate mixing, input impedance can be altered. By selecting appropriate sampling, output impedance can be changed. Once impedances are adjusted to appropriate levels, the performance of the amplifier automatically goes up. In addition, of course, negative feedback stabilizes gain, reduces noise, distortion, improves bandwidth. Those aspects, those improvements automatically come into being. In the present session, the focus is on type of mixing circuits, type of sampling circuits, and their impact on input impedance and output impedance of the amplifier. All these aspects we consider for discussion, for understanding. Now, let us move to begin the session. The session starts with a block diagram of a single loop feedback amplifier. Here is an amplifier. Its gain is A. It is associated with certain performance, and we want to improve, we want to enhance this performance further by applying feedback. Once feedback is applied, it becomes a feedback amplifier. So this is feedback amplifier, total thing. Single loop, only one loop is there in the structure. Multiple loops are also possible, but for most of the applications, for most of the required performance enhancements, single loop is sufficient. That's why we consider single loop feedback systems for study, for understanding, for analysis here. The signal source is there on the left hand side, the load is there on the right hand side. This is basic amplifier. Output has to be brought to input side for implementing feedback. Output is extracted with the help of a network. This network is called sampling network. The signal from sampling network is then passed through feedback network or beta network. Usually it is a passive circuit. The output of the beta network is called feedback signal. It is then brought to the input side and then combined with the output of the signal source. The resultant is then applied at the input terminals of basic amplifier. Here in this diagram, all the important parts of single loop feedback amplifier, they are shown. Feedback amplifier, a representation of a single loop feedback connection around a basic amplifier. The transfer gain A, here A may represent voltage gain, it may represent current gain, it may represent transconductance, it may represent trans resistance. A is a general symbol representing forward transfer gain of the amplifier. Now, a few points regarding the sampler configuration. Sampler, it is at the output terminals of the basic amplifier. Here we can see Here also we can see two types of samplers are there. One is voltage sampler, another is current sampler. Voltage sampler samples output voltage, or it extracts the output voltage of the basic amplifier and it gives that voltage to feedback network. Current sampler extracts output current and it supplies that current to feedback network. Depending upon our requirement, one can use either voltage sampler or current sampler. Voltage sampling reduces output resistance. Low output resistance is needed in case of voltage amplifiers. So, voltage sampling is the appropriate one in case of voltage amplifiers. Current sampling increases output resistance. Current amplifiers require high output resistance. So, current sampling is appropriate for current amplifiers. So, keeping in mind that voltage sampling gives low output resistance, current sampling gives high output resistance, one has to select appropriate sampler for the basic amplifier on hand. A few points regarding mixer configuration. Mixer is a circuit that exists at the input side of the basic amplifier. In A you can see, in B also you can see a mixer at the input side. Two types of mixers are there: series mixer, shunt mixer. Either one can be used, it depends upon our requirement. Series mixing increases input resistance. Voltage amplifiers require high input resistance. Therefore, appropriate mixing for voltage amplifiers is series. Shunt mixing decreases input resistance. Current amplifiers require low input resistance. So, appropriate mixing for current amplifiers is shunt mixing. It all depends upon our requirement. Depending upon the requirement, appropriate mixing, appropriate sampling has to be selected. An example, voltage amplifiers require to have more input resistance and small output resistance. These resistances, high at the input, low at the output, they provide more gain and more stability to gain. Hence, appropriate sampling is voltage sampling, appropriate mixing is series mixing. Similarly, for current amplifier, sampling appropriate one is current, mixing appropriate one is shunt. Similarly, one can select for transconductance and trans resistance amplifiers too. Here is shown a tabular form in which how mixing affects, type of mixing affects input resistance, type of sampling affects output resistance. For series comparison, one can see from this tabular form itself, table itself, RIF means input resistance with feedback. It is more than input resistance without feedback. For shunt comparison, RIF is less than RI. Input resistance with feedback is less than input resistance without feedback. So, series comparison mixing increases input resistance. Shunt comparison decreases input resistance. Here expressions are given for different types of amplifiers. As already mentioned, for voltage amplifier, appropriate sampling is voltage, appropriate mixing is series. As it is a series mixing, RIF is more than RI, it is equal to RI into 1 plus beta AB. In case of current amplifiers, appropriate sampling is current, appropriate mixing is shunt. As mixing is shunt, RIF is less than RI. In fact, RIF is equal to RI by 1 plus beta AI. 1 plus beta AI is more than 1, therefore RIF is less than RI. In case of voltage series also, 1 plus beta AB is more than 1, therefore RIF is more than RI. In case of transconductance amplifier, appropriate sampling is current, appropriate mixing is series. As mixing is a series, RIF becomes equal to RI into 1 plus beta GM. Similarly, in case of trans resistance amplifiers, appropriate sampling is voltage, appropriate mixing is shunt. As mixing is shunt, RIF is less than RI, it is equal to RI by 1 plus beta RM. Before going further, the point it requires to be kept in mind is input resistance of the amplifier. It can be altered with appropriate mixing. Now let us move to consider effect of sampling on the performance of amplifier. Sampling affects output resistance. Voltage sampling reduces output resistance. R0F is less than R0. Current sampling increases output resistance. R0F is more than R0. For voltage amplifiers, voltage series is appropriate one. R0F prime is R0 prime by 1 plus beta AB. What is this R0 prime? R0 is output resistance of the amplifier. R0 prime is parallel combination of load and output resistance of the amplifier R0. So R0 prime is R0 parallel RL. Similarly, R0F prime is R0F parallel with RL. So prime indicates parallel combination of this resistance with load resistance. So in case of voltage series, R0F prime is R0 prime by 1 plus beta AB. So notice output resistance has gone down. For trans resistance amplifiers, voltage shunt is appropriate one, as voltage is the sampling. It affects output resistance. R0F prime is equal to R0 prime by 1 plus beta RM in this case. Here also output resistance has come down. For trans conductance amplifiers, appropriate feedback is current series. Appropriate sampler is current sampler. For current sampling, output resistance goes up. For this case, R0F prime is R0 prime multiplied by 1 plus beta GM by 1 plus beta GM. The difference between G small m, G capital M is loaded and unloaded. For current amplifiers, appropriate sampling is sampler is current sampler, appropriate mixing is shunt. For this amplifier, R0F prime is R0 prime multiplied by 1 plus beta A by 1 plus beta AI. Here also A capital I, A small I. The difference between them is one is current gain unloaded, another is current gain when load is there in the circuit. Some more points regarding comparison and sampling. Voltage series, current series. Another two are also there, voltage shunt, current shunt. 4 types of feedback connections are possible. To begin with, voltage refers to sampling, series refers to mixing. First one is sampling, second one is mixing. There is another notation, another representation. According to that notation, voltage series is called series shunt. In this representation, first term represents the mixing type. Second one, sampling type. So voltage series is also called series shunt. Current series is also called series. In the first representation, first term refers to sampling, second term refers to mixer. In the second notation, first term refers to mixer, second term refers to sampler. Now, some points regarding voltage series. So first term refers to sampled quantity voltage and second refers to type of mixing series. This is also called series shunt. First term refers to mixing connection series and second one refers to sampling connection shunt. Now regarding current series, as already mentioned, this is also called series. First term refers to sampled quantity current and second refers to type of mixing series. This is also called series. First term refers to mixing connection series and second one refers to sampling connection series. Another feedback connection is voltage shunt. In another notation, it is also called shunt. Last one is current shunt. This is also called shunt series. A few points regarding voltage shunt or shunt. First term refers to sampled quantity voltage, this one. Second refers to type of mixing. This is also called shunt. First term refers to mixing connection shunt and second one refers to sampling connection shunt. When it comes to current shunt, as already mentioned, it is also called shunt series. The first term refers to sampling quantity current and second refers to type of mixing shunt. This is also called shunt series. First one refers to mixing connection, second one refers to sampling connection series. Feedback amplifier topologies. As already mentioned, 4 types of topologies are there. 2 are voltage series, voltage shunt. 2 are current series, current shunt. All these are shown here. In A, it is voltage amplifier with voltage series feedback. See, voltage series. B, transconductance amplifier with current series feedback. Here current is sampled, input side connection is series. C, current amplifier with current shunt feedback. This is current amplifier. Sampling is current, input side connection is shunt. TR amplifier means trans resistance amplifier with voltage shunt feedback. Voltage, this is a shunt. So here is shown circuits, equivalent circuits of amplifiers when voltage series feedback is applied. Voltage is extracted from the output side and it is connected in series with the signal source at the input side. Notice the feedback signal is voltage. This has to be kept in mind. Ri is input resistance of the amplifier. When there is no feedback, R0 is output resistance of the amplifier. When there is no feedback, R0F is output resistance with feedback. R0F prime is parallel combination of R0F and RL. RIF is input resistance after feedback is applied. Now, equivalent circuit of amplifier. When current shunt feedback is applied, the feedback signal IF, it is current. It is generated out of the sampled output current. This equivalent circuit is useful in deriving expressions for input resistance, output resistance with feedback in terms of input and output resistances without feedback. Notice in the previous circuit, source is denoted by a voltage, but here it is denoted by current. In the previous circuit, where voltage series feedback is implemented, the amplifier equivalent circuit uses a Norton equivalent at the output terminals. There, in voltage series, Thevenin equivalent is used. It is all for our convenience. Now, impact of negative feedback. Output resistance. Voltage series feedback decreases. Current series feedback increases. Current shunt feedback increases. Voltage shunt feedback decreases. Input resistance gets increased, decreased. Improved characteristic. For voltage amplifier, voltage series feedback is appropriate one. For transconductance amplifier, current series is appropriate one. Current amplifier, current shunt is appropriate one. For trans resistance, voltage shunt is appropriate. Why these are appropriate for these amplifiers? One example I will tell you. We consider one example. Voltage amplifier, as already mentioned, requires a high input impedance and low output impedance. Low input impedance can be achieved with voltage sampling. High input impedance can be achieved with series mixing. Therefore, voltage series is the appropriate. In the same way, current series is appropriate for transconductance, current shunt for current amplifier, voltage shunt for trans resistance amplifier. When applied voltage series feedback, it stabilizes voltage gain. Current series feedback stabilizes transconductance. Current shunt feedback stabilizes, desensitizes current gain. Voltage shunt feedback stabilizes trans resistance of the trans resistance amplifier. Bandwidth, what happens to bandwidth? Bandwidth increases. In all the cases, it increases. Reason is gain bandwidth product. It has to remain constant. When feedback, negative feedback is applied, gain comes down. Therefore, bandwidth has to be increased. Bandwidth has to go up. Similarly, nonlinear distortion decreases in all the cases. Certain critical information regarding feedback amplifier analysis is given here. Certain things are already covered. Some important points I will consider here. Feedback signal in case of voltage series is voltage. Current series is voltage. Current shunt, it is current. Voltage shunt, it is current. Sampled signal in case of voltage series is voltage. In case of current series, it is current. In case of current shunt, it is current. In case of voltage shunt, it is voltage. Signal source, it is Thevenin. In case of voltage series, current series, it is Thevenin. Current shunt, it is Norton's circuit. Voltage shunt, Norton's. One may get a doubt, why can't we go for Norton circuit in place of Thevenin, or Thevenin circuit in place of Norton? One can do it, but the thing is, analysis becomes complex. So wise men always try to do the things in the simplest possible manner. So desensitivity, it is 1 plus beta AV in case of voltage series. It is 1 plus beta GM in case of current series. 1 plus beta AI current shunt. 1 plus beta RM. This is desensitivity. Gain with feedback is AV by D in case of voltage series, GM by D in case of current series, AI by D in case of current shunt, RM by D in case of voltage shunt. We have already considered expressions for input resistance with feedback, output resistance with feedback, output resistance with feedback under load R not F prime. This also we discussed. Two rows which we have not discussed is 3 and 4. While analyzing feedback amplifiers, we have to follow certain procedure. To find input loop, set V0 is 0. In case of voltage series and current series, I0 equal to 0 in case of current shunt, voltage shunt. V0 is output voltage, I0 is output current. To find output loop, set V0 is 0, I0 is 0, I0 is 0, V0 is 0 for voltage series, current shunt, voltage shunt amplifiers respectively. These are some of the important things. In fact, these are critical things. Once these things are in our mind, it becomes very easy. It becomes quite simple to analyze feedback amplifiers. With this, we come to the end of the session. Before closing down, let us recollect important aspects we touched upon in the present session. The focus is on sampler circuits, mixer circuits, and their impact on the impedances of the basic amplifier. In addition, we have also discussed about appropriate sampler, appropriate mixer for different types of amplifiers, voltage amplifiers, current amplifiers, transconductance amplifiers, transresistance amplifiers. Hope this session is useful to you. We meet again in another session with a new topic.